Hey, we're currently live, got everything up and going right now. So if anyone's here, we're here to take questions, just holding a few office hours. And we'll be back later today with an interview. So I don't know if anyone's here right now. Might just talk over some of the topics real quick and see if anyone shows up. Still still not shaving. So if you are here, feel free to ask a question. We can do speed runs of it. I've got the speed run timer up, and I've got, how does this know? I wanted to start on this screen today. Thought it'd be fun. So we're over here on this screen and seeing how the green screen's working and everything in the new setup. Awesome. So we will just talk about a few topics real quick. Let's just talk about, to start, some of the confidence intervals you've learned. So if anyone's watching this later, this is just going to be a review of confidence intervals right now. We'll reset the speedrun timer for the moment. So when we do confidence intervals, there's a few things we need to know. And if you join the chat right now, feel free to ask a question. Hey, Brian, I'm stuck on this. Explain this better. Anything you want to hear, we'll go over. Confidence intervals, confidence intervals. So when it comes to confidence intervals, we have a few things we need to remember. Every confidence interval we make in this class, there are ones that follow a different pattern, have a center, and then the confidence interval also has plus or minus a margin of error. So this is kind of the general format we use, and understanding that everything after the plus or minus is the margin of error is key. And I see a lot of people sometimes, that's all right. It's a very, very common question. How do I find the margin of error if I'm not given like the standard deviation or p hat or things like that? We do have questions that we often give. Mike Pearson has a few where it might just say something like the interval goes from 6 to 10. So with the interval from 6 to 10, we have to think about what does the margin of error mean? So the margin of error is just a plus or minus. So I always ask people this. If, let's say, we're going to go to Chick-fil-A and it's going to cost between $6 to $10, what is the margin of error on this? And some people might say 4. That's not the right answer yet. But you have to think, I need to make a center of this interval, and then I need to do a plus or minus on it. So there's a few equations we can do, but let's not worry about the equation for the moment. Let's just think about how we would do this. To get the center of the interval, you just take the numbers and average them together. We can write the equation for that in a moment, but you're just going to average the two numbers to get the center. So think about 6 and 10 kind of colliding in on each other. That's what I do in my head, is I watch them collide in. And what number do they collide in on? When 6 and 10 go like this towards the center of each other, they would kind of mash in on 8. So 8 is the center of the interval. So now we write our plus or minus. We're just writing everything we would up top down here to write the interval as a plus or minus. And now that we have the center, we just need to think 8 plus or minus a certain amount of dollars. And you might notice something about this interval, that the margin of error is going to be half the length of the interval. We'll write these equations in a moment to find how this is written. So now we just write this. Now here's the big check you want to do. Once you write an interval like this, if you want to double check your work, if this is a test, you want to take the 8 plus or minus 2 and actually add and subtract 2. So 8 plus 2 is 10. That works. 8 minus 2 is 6. You've now written the interval as a plus or minus interval. So it's just another notation way of doing it. Sometimes we don't do the 8 through 10 or 6 through 10. We might do 6 comma 10 to show the interval. That's just another way of writing the interval also. The lower of the interval is 6, the upper of the interval is 10, or 6 through 10 is the interval. But knowing how to do this in notation is very important, and understanding what we have going on here with the center and the plus or minus a margin of error. So what are these equations that I'm actually doing? Well, let's put an equation for the center. The center is going to be the upper. So we've got here the upper plus the lower. Go and divide that by 2. That is going to give us the center. And the upper of the interval is going to be 10, and the lower of the interval is going to be 6. So that gives us 10 plus 6 is 16, divided by 2 is 8, and what are you doing? You're just averaging the numbers together. It's the bottom denominator is 2 because you're just dividing two numbers. So you add together two numbers and divide by how many numbers there are. That gives you the average of the two numbers. So all this equation does is average two numbers for you. It just gets you the center of it, kind of brings them like we just did in our head. So it's important to understand, why are we using this equation? What's the point of it? That way, if you are memorizing it, it makes more sense. It's like, well, what's the point of the equation? It's just averaging two numbers. So if you kind of memorize it that way and you say, okay, the center of the interval is just the average of the interval, well, then to average two numbers, you add them up and divide by 2. So we don't need to memorize it flat out. We can just memorize how it works and say, let's just average two numbers. The other one is going to be the margin of error. So the margin of error is half the length of the interval. So if you notice, I can give you any interval here. We could do it with a completely different interval. We could go, and I like to use whole numbers. We could use decimals, but you can do them in your head still, but much easier to use whole numbers. If we have an interval going from 50 to 70, so 50 to 70, we can also write it with the comma in the middle and put it right here. So 50 to 70. So if you're really good right now, you should remember that the center of this interval is just going to be averaging them. So you could do it with the math. You could say 50 plus 70. Let's write it right here. 50 plus 70 divided by 2 is equal to 120. Oops. When you add the top, it's equal to 120. When you average them, it's equal to 60. We all make mistakes. It's all right. So there we go, is the average of the two numbers right there. That is the center of the interval. And now you should try to figure out the margin of error. The margin of error on this is going to be 10, but let's think about what the margin of error is, because that's what we're trying to understand right now. The margin of error is half the length of the interval. So what is the length of the interval? So we need half of it. The length of the interval is 50 to 70. So that's the length of the interval. Now we can do this mathematically in a moment, but 50 to 70 has a length of what? 20. Now we need half the length of that interval. 20 divided by 2 is 10. So when you remember that the margin of error is half the length of the interval, you know what you need to find, the length of the interval, and then find half of it. So mathematically, the length of the interval will be the upper minus the lower. And just think about this, what is this getting you? Just how far out those two numbers are apart. So this is just going to tell you how far away those two numbers are from each other. And then we divide by 2. Why are we doing by 2? You should be saying because the margin of error is half the length of the interval. So we have the full length of the interval, we divide by 2, we get half the length of the interval right here. And half the length of the interval is equal to 10. So now we know the margin of error of the interval. So that gets this right here. I've had this highlighted the whole time, but the margin of error of the interval is 10. It's just half the length of the interval. And that is for symmetric intervals like this. I don't know if you're like, well, what about a chi-squared interval? Well, it's going to have a little bit different of a shape to it because the chi-squared distribution is not symmetric. So you stats people out there, knowing that extra stuff about the chi-squared intervals for the standard error, or standard deviation, excuse me. But we can write some intervals right here that we do in our class. We could write some intervals like y bar plus or minus a t statistic with n minus 1 degrees of freedom. We put a star right here, which means you get to pick that t, and then we do s over square root of n. Now, the biggest thing you should do right now is you should notice we've been talking a lot about the margin of error, and the margin of error is everything after the plus or minus. So what's the margin of error here? You should pause and say, okay, what's the margin of error? The margin of error has to be all of this. Look how it's in the same exact spot as that plus or everything after the plus or minus. So we've identified what the margin of error is, but let's identify all parts of this equation. So we know from our notes above that apply to all the intervals we're going to talk about that y bar has to be the center. All the intervals we make, the center comes from a sample. The sample is kind of a estimate of what the truth is. So let's look at that y bar. Y bar comes from a sample. Is that true? Yep. Y bar is the sample mean. That comes from a sample. It's the sample mean. It's like you went out and collected the heights of individuals, the weights of individuals, the GPAs of individuals. These would be just samples from people, and you would get a mean when you average the data together. So this is the sample mean right here. If you're in the chat, feel free to say, hey, we're just reviewing kind of concepts for confidence intervals. And then what do we have next? Well, everything after the plus or minus is the margin of error. And what's in the margin of error? The margin of error has a t statistic, and this is subscript right here, and that's superscript up there. The t comes from the t distribution. It's going to get us our confidence level. So we can say, like, I am 95% confident. I am 90% confident. And so let's draw a little t distribution right here. We don't know how many degrees of freedom it has, but every t has with it degrees of freedom. It's kind of like the normal curve. It's a normal curve with extra variation on it, fatter tails and everything. So we have here the t with a certain amount of degrees of freedom. Put the subscript down below it. Make it look more like a subscript. And this t right here will control our confidence level. So when we do this right here, we could do a 95, and it'll tell us, we'll have to use an applet or something like that to tell us if we're doing like a 95% confidence interval, or if we're just doing the middle 90%, we will look and we will have the right amount of area in the center of it, and that'll tell us. Now there's other ways to do it where you could put the area on the outside. With the age of applets, I like to just put the area in the middle. So we could have here 10% on the outside, and if you do 10% on the outside, that would be a 90% confidence interval. So with this right here, we can get the t-statistic, we can shade the outside of it or the middle of it to get this down here would be a 90% confidence interval. And what does the t tell us? The t tells us our percent confidence. There's a star on it because we get to pick it. So we can say, I want to build a 90% confidence interval. I want to build a 80% confidence interval. I want to build a 95, I want to build a 93, and that'll change what the t-statistic is, and it'll move it further or closer out. Now, more confidence means a wider interval, and so when we think about this right here, we can choose our interval to be really wide, like 99% confident, but then it's going to be not so precise. It's going to be less precise because it'll be a wider and wider interval, but it'll be more confident. More confident means less precise. Less confident means, more confidence means less precise. More precise means less confident. So we can see this right here. But we can increase the precision by increasing one last part here. We can make our confidence interval tighter with one last thing right here. And let's not erase. We'll just, we erased it. We'll write that t again. T with n minus 1 degrees of freedom. And so the last thing we can change if we're starting out collecting data is our sample size and our standard deviation. Now we don't really control the standard deviation. I mean, if you were to like explicitly take individuals, which you wouldn't want to do, you want to do random, condition 1, take your data randomly, but we don't really control the standard deviation. The data kind of controls that. We do control how much data we take, so that is something the researcher can have control over, this part of the bottom of the equation right here. So the sample size, n, is how many individuals we sample. So we could sample 100, we could sample 1,000 individuals, 5,000. That is just how many individuals we sample right there. And then S is the sample standard deviation. So on the bottom of the equation, we have the sample size, and then on the top of the equation, we have the sample standard deviation. So we've got all this right here, and then a question would just tell you this information. Like the question could say, we went out and spoke to 100 students. They had a sample mean height of, let's say, 68 inches. That's the sample mean right there. With a standard deviation in the sample of 2 inches, we want to build a 95% confidence interval for this. Now I'm going to take a guess, and actually I think I've got a pretty good guess. I think it's about 1.97. And I'll have to hop over screens here to show you. With 100, might be 1.98. We'll find out. It's for anyone statistician watching this. I keep saying this like statisticians are watching my videos. But we all know the z-score for a 95% confidence interval is 1.96. And since there's a lot of degrees of freedom, the z will be close to the t. So the z's are kind of like the t's, or excuse me, the t's are kind of like the z's, but the t's are fatter. I always say Mr. T comes in and says, I'll pay the fool, and smashes it down. So it's got the wider tails. So that's going to make your intervals a little bit wider, and you really notice it when you have smaller sample sizes. So the t's drastically differ from the z's when the sample size is much smaller. As we get more and more degrees of freedom, they get closer and closer to the z. And we'll show this right here. I will show the answer of how I got this, so it'll take just a moment. I'm going to go to one of my favorite sites, statdistributions.com. Don't know who made this. Might say at the bottom, Nathaniel Johnston. Thank you, Nathaniel. Excellent site. Let's go over here and take a look. We'll bring it down here so we can all see it, and I'll put it inside the window. Oh, it went big, and we'll need to make it smaller. Let's see how it's looking on the screen right here. I'll size it up for the window. And so we can see it right there, and let's go here. There we go. And let's go here. 2 seconds. We'll get this nice and good. There we go. Okay. Good deal. And so we can see what's going on, and we can build our distribution now. So let's take a look at this. To build our distribution, we are going to say that we have how many degrees of freedom. And so I think I wrote this in the equation just a moment ago. I can show it off right here. The equation has n minus 1 degrees of freedom, so we need to do the sample size minus 1. The sample size was 100, so you should be thinking, how many degrees of freedom does this have? 99. It has 99 degrees of freedom. So this is where we put in the degrees of freedom right here. 99 degrees of freedom, and and then we already got it. 1.97. I've done this one a few times. It's I don't know, it's an easy, but did I enter in 199? That'll be wrong. See, that's never congratulate yourself. It's 1.98. I was thinking it might be that. So very close, off by a decimal. So for anyone who is working this problem, make sure you change this. You could carry the 2 if you want, but 1.8 should be close enough. But technically, I guess let's do it totally accurate. From here, it becomes an algebra problem, and it's just solve it. And I guess you know what? We're here. We'll solve it. So we got 1982 right there, 1.982. And let's just go ahead and solve this with our calculator. So we bring up our calculator right now. Now here's the way I like to solve these things, is I like to do the very right side of the equation first, the margin of error, because we're going to go ahead and solve the standard error, which that last part is the standard error. S over square root of n is the standard error. So we take 100, we take the square root of that, it's 10. Should have just said that. And then we take 2 over 10, that's 1/5. So we do 2 divided by 10, that's 1/5. This is a really nice example problem right now. So we've got 1/5 times that, 1/5 of that is going to be about 0.4. Should try to figure out the rest of it. My brain is slowing down today. Is it 0.398? Let's figure it out. So 1.982 times 0.2, 1.3964. So very close to that. It's basically 0.4. But we go in here, 3964, and do 68 plus or minus 3. Nope. Missed the decimal. There we go right there. Make sure your numbers are correct. It's so easy to miscopy a number, especially when you have things on separate screens. I do it all the time. Probably the easiest mistakes we make are just writing things down the wrong way. So it helps when you have an actual physical calculator and you look at it, it's not on a separate screen. Here we are, we've got our numbers. Now what we can do, we can go ahead and take these numbers, and just for ease of this problem, we're going to round this to this right here. Now it's a super nice problem, just do a little rounding on it to 2 decimals. And because everything, if you notice, kind of rounds up right here. We've got the 6 rounds up, and then we've got the 9 rounds up. So all of this rounds nice and neatly to just this right here. And now it should be really easy to solve this in our heads, and that's what I like. I like problems we can look at and kind of understand how they work, because now we can rewrite the interval. And all we're going to do is going to add and subtract that 0.4. So when you add 0.4, you get 68.4. 68.4 is going to go right here, and then the lower bound of the interval is 67.6. So this is our interval right here, and if we were collecting the heights of students, I would say I am 95% confident the true mean height of students is contained in the interval 67.6 to 68.4. I am 95% confident that the true blank is contained in the interval blank to blank. I am 95% confident the true mean height of students is contained in the interval 67.6 inches to 68.4 inches. And that is how we do our intervals. This is how we solve the mathematics. This is how we write them out, and how you can do example problems. Just practice doing your own problems. Get good at just writing them out, knowing how they work mathematically, and you will get better and better. Let's just write our last few equations right here. Here's all the interval equations we have seen. All the interval equations we have seen are an interval for the true mean. Notice that an interval for the true mean, the one we just did, starts off with an estimate from the sample mean. So wait, this next one is an interval for the true proportion, because an interval for the true proportion starts off with an estimate from the sample proportion. So kind of rewind the tape right there and be like, wait, the first one was an interval for the true mean with an estimate from the sample mean. This one is an interval for the true proportion with an estimate from the sample proportion. This one uses z, and then we have here p hat, q hat over n square root. And then last but not least, the other interval we do in this class is going to be for the difference between two means. So if we're trying to find the true difference between two means, we would have here the sample difference between two means. Now here's the confusing thing. This is the first part of this interval right here. This part is the same as all these other parts right here. I know it has 2 things in it, and you might not always see people put it inside parentheses, but it's the same position. It's the thing we're trying to estimate. It's the center of the interval. Because what's our best guess of the true difference? Well, the sample difference. Plus or minus. The degrees of freedom formula here is very complicated. We don't solve it by hand usually. It's a complicated formula. That's oftentimes the test question. Not that it will be. But it's a complicated formula that we use applets to solve for. It's got about, I think, like 8 components in it. I can maybe show it here in a second, but it's a very not fun formula to solve. I'll put it on the screen here in a moment. And then the last part, you see that's where the t is. Last part is the standard error of the difference, and the standard error of the difference is going to be Let's see here, S1 squared over N1 plus S2 squared over N2. So if you're wondering how I know this, it basically follows the format of this right here. It's not the same thing, but we're taking and adding together the standard errors. We're adding the standard errors together from the first sample and the second sample, but you'd say, wait a minute, that one up top isn't S squared, it's just S. Well, we're squaring them, and then we're adding them together, and since we squared them, we're square rooting them at the end of this. You don't need to memorize these. We give you these formulas in the class, but if you understand how it works, maybe that's how I memorized it. It's like, oh, the original one is S over square root of N, which is kind of the distribution getting tighter as N gets larger. That's the central limit theorem coming into play right there. As N gets larger, the standard deviation is going to get smaller. So this is the standard error, and it's going to turn the standard deviation, which is up top, is going to become the standard error, and the standard error gets smaller as N gets larger. Once again, just to make it very clear, this right here is the standard error of y bar. This right here is the standard error of the difference between the two sample means. Standard error of y bar 1 minus y bar 2, and that's subscript. So these are standard errors right here, and the standard errors will get smaller as the sample size goes up. So understanding that that last component, and this is a standard error 2, standard error p hat. So that standard error is basically your uncertainty in it. We talk about that a lot in 320, but it's just our uncertainty in the estimates. And so we got all that right there. So I did promise that degrees of freedom formula. Let's look at that degrees of freedom formula and see what's going on with it. What is going on with the degrees of freedom formula? It's a crazy, crazy formula. Someone will be like, wait, Joe, let's go ahead and grab that degrees of freedom formula. 2 seconds, we will show it. So degrees freedom to sample t test. Okay. And the degrees of freedom formula is, where people have graphics of it. This is one I do not memorize. Oof, there it is. Okay, let me take a screenshot of this. Just messed around with the timer right there by accident. So let me take a screenshot. It's probably way off center now. Oh no, I fixed it almost. There we go. Okay, so let's take a look. Wrong button. What is this? Back one page. Okay, let me take a screenshot of this. And where's my screenshot tool? Okay. The degrees of freedom formula will be here in just a moment. One of these days, well, I don't know. I memorize a lot of things, but this would probably be one of the least helpful things for what I do. We want to go to wrap text, behind text. There we go. Now it'll. Oh, I always forget. It's like, I wish it just said what it would do. Did I not put behind text? Yep, that does what it wants. Good. And so here we go right here. Here's the degrees of freedom formula. Do not solve this by hand. This will tell you the other one's way easier. It's just n minus 1. All these, there you go. It's just n minus 1 right here for a 1 sample t. And for this one, it is crazy, crazy, crazy. A lot going on right there. So we have right here just a very, very large formula for the degrees of freedom. And that is the degrees of freedom on this one. But for this one, the degrees of freedom are n minus 1, which is way, way easier to solve for. N minus 1 is just the degrees of freedom inside of here. So, whoops, space, well, that's weird. There we go. So this one is the degrees of freedom here, but the degrees of freedom is test dependent. So make sure you choose the right degrees of freedom. And I think it's kind of just wanted to go over this and put a video out there this morning with this. We'll be back broadcasting all shipments. So we will be back broadcasting here later today. We'll have the interview with Julio. So if you were watching, I don't know if anyone swung by this morning, but if you were watching, say hey. I think maybe the later in the day streams are better for people. But if you're here, say hey. I don't know who's watching, but we're going to head off. If you have questions, feel free to email me them. I'll be back streaming later, and I hope tons of people come by for the interview. So we'll be back later today. So I'll see everybody then.